G'day everyone, and welcome to our lesson on voltage, current and resistance. In order to explain what voltage, current and resistance are, first of all I'm going to introduce a concept, charge. And we hear about charge a lot when we're dealing with electrons because electrons are charged. And charge is the basis for electrical circuits. So we've got this idea of charge. Its symbol is Q and its units are coulombs. There we go. So as I said, we know about charge because when we deal with electrons and protons, we talk about them being charged particles. The current in a circuit is made up of charged particles moving around that circuit. So if we have a battery, a resistor, and that wire there, if this is the positive side of the battery and this is the negative side, we'd expect charged electrons to move around the circuit through that wire in that direction there. But a coulomb is not the charge on one electron. One electron, there are billions, trillions of electrons in everyday objects. So one electron doesn't carry much charge by itself. In fact, one electron is only 1.6 times 10 to the negative 19 coulombs. So you would have to have 6.25 times 10 to the 18 electrons to equal 1 coulomb. So that's how we talk about electrons and charge. One electron is 1.6 times 10 to the 19th coulomb. So you'd need 1 over that electrons to get that 1 coulomb worth of charge. So that's how we talk about charge. And we said charge is moving. Now if you were standing, say, by a river, and you wanted to know how fast that river was flowing in that direction there, you could put a gate there, and you could measure how much water passes that gate per second. And if you knew that, you could basically work out how fast the river is flowing. The same concept applies to circuits. If we take a certain point here on the circuit and we measure how many electrons flow past that point per second, we can figure out the current in that circuit. So we have this idea of current. We use the symbol I, and it has units, amperes or amps, which is A. And amps, if we said it's the amount of coulombs or charge that passes a certain point per unit time, amps is the same as coulombs per second, the amount of coulombs that pass that point. So it's very easy, if you understand what a coulomb is, to understand what current is. It's just the movement of coulombs, the movement of charges around the circuit. Let's introduce voltage. The symbol is V, and the units are volts. Big V there. It's common knowledge that the voltage for any circuit, for this circuit we've drawn here, or for things like a Game Boy or an iPod, is supplied by the battery. We said there are these charges moving around the circuit. The voltage gives energy to the charge. So in actual fact, the definition of 1 volt means each coulomb, so each charge, gets 1 joule of energy. And this is very neat because 1 volt is 1 joule per 1 coulomb. And this clues us in. Why have we used this coulomb, which seems like a very artificial measurement? The answer is it helps our formulas match up with energy, which is a Newton meter. Without that coulomb charge amount here, we'd get very strange energy measurements, which we don't want. So the volt, say this is 5 volts. That means every coulomb that goes around that circuit, every bundle of 6.25 times 10 to the 18 electrons, but of course we know they're in a line, each coulomb or group of electrons receives a total of 5 joules of energy. And if you studied the light and matter unit, you'd also know that you could say that each electron gets 5 electron volts worth of energy. But the voltage is basically giving energy to the charges. Now we'll introduce this idea of resistance. So we have voltage, which gives the energy to the charges, the current, which measures how many charges pass a certain point per unit time, and now we're going to talk about resistance here. Resistance has symbol R, and its unit is the ohm, which is given by this funny little symbol there. So I'll draw that very neatly. And resistance basically measures, for a given voltage, how much current you're going to get out of a particular circuit. So the law is Ohm's law. V equals I R. We understand voltage is the energy given to each coulomb. I is the number of coulombs passing a certain point per unit time. And resistance is what relates these two things in a circuit. Let's do a quick example. Say we had 5 volts up here, and the resistance down here was 2 ohms. By changing the resistance and the voltage, which are very easy to change, we can actually change the current through this circuit. So 5 is equal to I times 2. Divide both sides by 2. I is equal to 2.5 amps. Now, this relationship here, V equals IR, it's supposed to apply not only to the circuit, but to each individual component as well. It always applies to the whole circuit. The total voltage is equal to the total current times the total resistance. But there are such things as non-ohmic devices. So we have, I'll move this over. We have ohmic devices and non-ohmic devices. And ohmic devices basically have a constant resistance. So resistance is constant. So if I were to graph, I'll rearrange this formula first of all. So I have V on R equals I, or 1 on R times V equals I. If I graph then I versus V here, V is on the horizontal, I is on the vertical, so the gradient is going to be 1 on R, like that. And an ohmic device will have a straight line, because if R isn't changing, 1 on R is certainly not changing. So that's what an ohmic device looks like when you graph the voltage against the current. A non-ohmic device has a varying resistance. So if I graph now voltage against current, I might get this here, or I could get something like this. Oops, sorry, I think they're all supposed to start from down here, like this, or like this, or like this. And what it's basically telling me is that the gradient of these lines is not staying the same. So 1 on R is not staying the same, therefore R is not staying the same. So when you have a varying resistance, you get weird, curvy V versus I graphs. So that's the difference between an ohmic and a non-ohmic resistor. New concept, power. Symbol P, unit watts. Power is the energy released per unit time in a circuit. And there are a few key formulas associated with it. Say I have this resistor here. We said it had current 2.5 amps flowing through it. The amount of power that is being, we say, dissipated in that resistor is equal to VI. So in this case, power is equal to voltage. 5 volts will be dropped over this resistor here, multiplied by the current. So 5 times 2.5, 12.5 watts. And watts is another way of saying joules per second. That's not the only formula for power. We have VI, we also have I squared R, and we have V squared on R. The reason for this, we start with P equals VI. And we also know from here, V equals IR. So if we get V by itself here and we sub that in down here, we have P equals IR times I. That's I squared R. And that explains that formula there. Alternatively, P equals VI. If we get I by itself over here, so V on R equals I, we can, I appears here, so we can sub these in where that I was. P equals V times V on R, or V squared on R. That explains that formula right there. So we'll try an example question working with power. I have a battery, a circuit, a resistor. The battery is 5 volts. The resistance is 10 ohms. The current flowing through this circuit I is equal to, well, we rearrange to get I by itself, that's V on R, which is equal to 5 on the resistance total of the circuit is 10, or 0.5 amps. Let's figure out how much power is being dissipated here. So we can use one of 3 formula here. P is equal to VI. Well, this is V, this is I, so we think 2.5 watts, 5 times 0.5. Or P equals I squared R. That would be 0.5 squared times 10, or 0.25 times 10. That's 2.5 watts. Or we can use P equals V squared on R. That would be 5 squared on 10, 25 on 10, or 2.5 watts. It doesn't matter which power formula we use. We're always going to come out with the same answer, and this is a great way to check your answers. If you're in ever the exam situation, you've got one of these questions you're not sure of. Finally, I'll just mention energy. E, the unit is joules, and we find energy by multiplying by power by the time. So this circuit here will say how much did this circuit release over 10 seconds. Energy equals 2.5 times 10, or 25 joules. 25 joules is dissipated in this resistor over 10 seconds. So to summarize, one charge is a bundle of electrons or positive charges. It's a certain amount of minute charges that make up a single coulomb. Current is found by the number of charges passing a certain point per unit time. Voltage is the amount of joules or energy given to each charge. Resistance relates the current and the voltage in a circuit via Ohm's law. Power can be found by one of 3 different formulae. And if you want to find the energy, all you've got to do is multiply the power by the time you're looking at.